Okay, so when you have time, just update your toolbox because there are several updates that we really need in order to run today's example for regression. So you need to switch to the correct folder where your old version of your toolbox was installed, and then to run this, to unzip, download. Okay. As I said, the most important line of the code is just this one.
Can you just copy paste that?
Yeah. So yeah, if you know what the code is doing, maybe you just copy this one. Yeah, it's fine. The rest of them just the first time you probably need. Okay, we will look at regression problem, and this is the outline of today's session. We'll start to look at the regress function, built-in function in statistical toolbox in MATLAB, and then the regression learner, just like the classification learner we used before. This is a user interface provided by the MATLAB environment to allow you to, through the click, to select different models of regression and see what we can do with this. Then we will look at some real data set to run regression. Okay, for that one, we need X matrix and a Y response variable. Then we will look at this highly variable gene expression analysis. If you are given a set of the cell, and how can you identify those highly variable genes, as we described in the lecture. Those genes are important, right? At the end, we will still have time to do the lasso. Lasso will have very similar function call structure as regress. But because it gave you the regularization panel, so you have the way to select the variables that you want to include in your final model. So we will see how to run lasso, and probably we have some examples, use real data set to run lasso. Okay, any questions? Okay, if you just came in, you need to upgrade your toolbox to the latest version. Just make sure. Yeah, I just double check everything works fine. Okay. All right, so we will look at the function regress. So if you see documentation regress, so let's see which regress. So this function is located in toolbox statistics. So this is a very basic function. If you do doc, you will see the documentation. See how are you going to use this function. We will play with example data set provided by this documentation. Okay, the syntax is easy. the problem is you want to estimate the beta. Beta is the parameters for each variables in order to give different weight to explain y parameter. So your input is y, x, big X, and b. So you want to build this linear regression model. So to have y equal b times x. Okay. So this is a vector. So it's n by 1. This will be vector p by 1. Depends on whether you have this beta 0 in there, or it could be the p plus 1 times 1. Okay. And x is a matrix n by p. If p equals 1, you have a simple regression. Okay, if you have a more than one variable, so p greater than 1, you have multiple regression. So in this example, we will use two variables, x1, x2, to explain y, the mileage per gallon. Okay, we copy this and put into here. Okay. So this is an example data set built in the MATLAB provided for your convenience to have some data to play with. There are multiple properties for 100 samples of car. So in this example, we want to use x1, x2, two variables to explain the y. Okay. If you have a data set like this, you can start with a scatter plot. Okay, you want to scatter x1 against y. So just look at the figure to give some idea of whether there's relationship between one variable versus another. So in this plot, scatter plot, we have x-axis is the weight of the car, and then you have y as mpg. So it makes sense because the larger car will be more less efficient mileage per gallon, so it makes sense to us. Then you shut this down and you can plot 2 to mileage per gallon. Also, this negative correlation. You can see the trend. Then come back to this documentation. The next, you want to create a matrix. Okay. Put x1, x2. Yeah, in this case, we can ignore the interaction term. Okay. So if you believe there nonlinear interaction between x1, x2, you can add this in. So this is just product of these two variables. As an independent variable, you include 3 variables. One of them is composed variable by the product of x1, x2. So this is a way to do this interaction term, but our example, we can just copy the non-example part. Okay, that's easy to understand. So if you put that three terms in, you create a matrix X. So this matrix contains one column 1. This is for the intercept at the end. And then you have a first variable, the weight, and then the power, the second. So you put these 3 columns in, these 3 columns and 100 samples. So we are constructing this big X here, okay? Where's my pen? So now this big X contains 100, so N is 100, P is 2. Okay. However, this constructed contains 3. It becomes 100 by 3 because this 1 in there. Okay. Okay. Any questions so far?
The size, X1 means how many X1?
Oh, the size. If you take this out, this will give you the dimensionality of size X. So this is 100 by 1. So it's just tell you, yeah, how many columns, how many rows you have. Yeah. So if you give this 101 to this function once, so if you do once, say, okay, I want to 3 by 1, it will give you a list of 1 by 3. But if you give 100, it will give you a long vector. You don't have to type that. Okay, so just create a vector contains 100 ones, basically. So there's this part. Okay, we have X here. Let's see whether they have a missing data. So here we have a missing data in our original problem. So this has to be removed. Yeah, so in this program here, it doesn't care whether. So this function supposed to be tolerable to missing data. If you don't, if you didn't know they're missing data, the function should take care of this, get rid of those internally by itself. But what I want to do is to remove this manually. So let's see. If I gave 2. So this is a row 77. So I will remove that. Instead of using 100 rows, I will use 99 rows as my input data. So anyone can tell me how to do this, how to remove this row 77 from X. So that's the way you can pick the row 77. Okay. So if you do this, you will get this particular row here. But if you set this into nothing, then this row will be removed from the original X matrix. Now this X matrix right now is 100 by 3. After you remove it, it will become 99 by 3. Okay. Remember, we still have to remove the Y as well, 77. Because right now the paired variable Y will be 100 cars, but here you have 99, it's not matched. So we remove this particular element in Y77 again. So now we can build our regression model using X to predict Y. So in that case, you can just copy this, and that will give you the Y, the beta. Okay, give you three numbers. First is the one associated with all ones. So this is intercept, and then you have two negative values to indicate the relative contribution for each of x1, x2 to explain the y variable. Is that clear? Okay. Yeah, we cannot copy this because we don't have this interaction term, okay? If you want to copy, you can copy it to here, but not this part, okay? If you want to copy this, because we are using just two variables without the interaction term, because we didn't explain what the interaction term is. Okay, so I will come back to this PowerPoint. So if you have now if you have x and y, you want to solve the problem by regression to predict the beta. So as I said, the equation was like this. Then if you do linear algebra, B will be x transposed and times y. So we are going to try whether this will work for our example without even using the regression. So what I will write will be inverse x times y. So that's not working, so I have to do the so-called pseudo inversion. Not working. I will try our normal equation. Yeah, so here, so on this slide, I have several examples. If you have x and y, you want to do the linear regression, there's some kind of shortcut. And if you do this, it's supposed to work. I don't know why I gave you so many non-zeros. Okay, I believe in the data set we still have non-negative values, not numbers. So I have to check here. In the y, okay, yeah, so that's a problem. So in y, we still have some not numbers. We have to remove them in order to make all the algorithm working, okay? Quite a lot, yeah. So we have to remove this not a number. So that's what I'm going to do. Okay. So if I found all the not numbers and then remove them with index from x. And then I remove them from y, okay? So if you have a way to, if you manage to copy these 2 lines of code, this will check whether y has not a number in there, missing data, and then remove from corresponding rows in the x. So in that way, we really clean the data. Otherwise, the way I'm trying to do it just not work. Thank you for Jakarta. Now the data is really clean now. It's only have 93 cars. Okay. Anyone need more time to finish this step? So we still run this beta regression, and then you still get the similar results. Should be similar or should be the same as before, right? So to use this to compute beta, so we can try use the inversion, the pseudo inversion to do this. Okay, the inversion, that function does not work for the non-squared matrix, so we have to use p. Basically, you invert the matrix and multiply it by y. This produce the same answer with the regression. Okay. Is that okay? Yeah. So so this tells you the relative contribution of x1, x2, and their direction, whether increase or decrease y's value. You can also write in this way, okay? So this is the normal equation. So the normal equation writes like invert, okay, invert x transpose times x. I hope this is correct, because I'm not so sure whether the input should be variable by sample or sample by variable, but this should work. Okay. So this solution is using the normal equation to solve this linear regression problem. This operation is so common, so MATLAB actually defined an operator, so x / y, and to give you directly the answer, because engineering uses so much, and so you can have x backslash y to get the beta value. Okay. Okay, let's look at this regression learner. If you copy this regression, okay. Okay, so this is interface. Let's start with a new session, and you want to have some variables. So they're either from the files or from a workspace. We have our x, y, so we just from workspace, we know what we are doing. Then here you have to select the input, what's the data set. Okay, data set was. So we use columns as variables. And from workspace, we have y as your. Then you don't need the first column because the first column is all ones. So yeah, you should just set up your environment like this. You select your x, use that as a input variable, and then use response variable will be y, okay, lower y. So in that way, you just tell the regression learner, okay, which variable you want to predict for, you build a model for, and then what's your input data is. The big X matrix is in there. Okay.
So X is your input data, Y is your predict.
Yeah, you want to use everything in the X to predict Y. Now if you put into the single cell data analysis context, that will be X will be the whole expression matrix of many genes, and then you want to predict Y. Y could be some features of the cells.
But you cannot select Y. How can you select it? If it's a single cell data, it's a matrix file, right?
Yeah, but you can still read the matrix file into memory.
Into the GL.
Yeah. You can put it into it as X. I show you how you use examples. Yeah, but that's the way you have other ways to prepare your data set. If you have a CVS files, Excel spreadsheet, you should have a way you can find a way to put that in. Then you should start the session. So there are all different kinds of regression, linear regression models. Okay. Just select the simplest one and then train them all. Mhm. Yeah, so this is a linear regression model. I don't know exactly yeah, result table. I'm not very familiar with this interface. I don't know exactly where the parameters they predicted is located. Um, but this plot shows the input data that's in blue dots and then predicted for each of the samples. Uh, yeah, I'm not so sure how to look at this, but that's the interface they provide to do this regression models. Maybe I should try. Oh, yes, I think I know because I was confused with why I didn't see the regression line. This is not because we have x and two, x1, x2, so it's not a simple linear. Y and y hat, yeah. This is plot. This plot, yeah, it's not a linear. Not just one single line. Yeah. So this is just show you the difference between your predicted and observed.
Yes, there's a line.
This one here?
Yes.
I can click this?
Yes.
Oh. Oh, yes, this is scatter plot of the predicted with true, yeah. Yes, this can tell you how far away your prediction offsite from this expected. So if you have a perfect prediction, all the points should be on this perfect prediction line here. You're right. Okay, any other questions? If you have a data you can organize in the way that you can put that in this, you probably can have a lot of different ways to click buttons to learn more about the different more complex models. Okay, should we move on to next topic? Yeah, now we will use real data set to make X and Y for ourselves, see whether we can apply some of those techniques we just learned to do some real work. So I clean all the workspace. Okay, now I'm going to construct my own X and my own Y, okay? Because I just assume once I gave you X and Y, you know what to do next, all right? So we will use single cell data toolbox. Then maybe just example data. Processed will be great. So let's focus on one cell type here. Okay, which one we should focus on? Okay, I click this button to separate the cells into different groups. I separate them by cell type. I'm not going to manually order the names, but by just by size. Okay, in this figure, I have most. Now here I have fibroblasts, 1,000 fibroblasts. Yeah, I think I will just extract fibroblasts out from this data set, and we will work on this, okay? So what you can do is just click this, make a new SCE, say fibroblasts only. Okay, if you have a problem, let me know what we are doing. Just look at different cell type, and I found fibroblasts have enough cells and looks all right. I want to extract the fibroblast out. That's what I'm doing here. Once you have this interface, you can shut down the rest, the old one, the old fibroblasts. So now we need to do the QC again, to do the basic QC stringent. I have a cluster of cells. They belong to fibroblasts, but because away from the majority of other fibroblasts, I will delete them, remove them. Yeah, you can use stringent. Yeah, normally stringent will be okay. So I want to remove those cells. It's small clusters. I can brush it and say delete. Delete selected. If you select unselected, you will delete all the other cells, but only keep those ones. You don't want to do that at this moment. You delete the select cells. Okay, now the cell looks as a group. Give me a little bit more confidence. They are fibroblasts. Okay, there are no outliers, and I do this QC again. To remove 26 genes. Okay, now I will save this as a temporary fibroblast cells. Okay. So this just in case something happened, the crash, the program, I still have the data set I already processed to load it back. Now you can export, let's do, because we want to use the expression matrix, so it's very easy to export X matrix. So you can just select this and see, I want to export X matrix. So this matrix will be out easily, but we don't have Y matrix vector. So this will give you the matrix 9,324 by 1,299. That's X matrix. But we need a Y matrix. I want you to predict the cell potency, differentiation potency. So in order to compute that, you need to do this cell score, because that potency is assigned to every individual cells. So we need a vector of the variable are the cell Ys. Okay, so we need a value for Y. So let's click this button here, and then you want to compute a particular score, and this score you are not going to compare between samples. We just compute the score for each cell. So in this here, you select differentiation potency. Okay. So this potency tells you whether this cell state is more close to the stem cells or not. Stem cell will have a really high value for this. Highly differentiated cell will have a very low differentiated potency. Okay. If you want to know more about this computation or what algorithm behind this, there are PubMed paper describe this algorithm, but we just compute these values for every individual cells. Okay. So now we just click this. This is introduction of the method. Our data is mouse data, so yeah. So this plot to show you the values of each cell, their differentiation potency. Some cell in this corner have a really high value, and the color is more yellow, while the other place, the cell have a lower values. Okay, this create a gradient then as Y variable. We want to use X or the gene expression to predict Y, see which gene can be used as the most contributing variables to explain the variability of Y, which is differentiation potency value across cells. Right? So we need to you can export, let's export these values into workspace. This will give you a table, okay? This table contains 1,299 rows. This number is not random, is because you have 1,299 cells. So each cell has a value here. So after you finish the computation of the potency value, you can close this, and now we can export the X matrix. Now you select X. You can still keep this checked. So once you save this, you will have X matrix. You will have your differentiation values. Okay, that's all we need. So I shut this down. Anyone has any questions what we are doing here? We try to build big X matrix. I want to have a Y matrix. Okay. So the Y matrix is inside this table. Okay. So this table is called DIFF. Differentiation policy, this table. So I want to export this value to, you put a dot here, and then you have a CS, this is called sales score, okay? So this line of code is just have that table and give me the column called CS. The value will be out as a information of the numbers. Okay? Yeah, basically what I just copied basically this line and make this Y variable. Now we have X and Y. We need to transpose X because right now the X is by variable, feature variable by sample. We need a sample by feature variable. Okay. But before that, I would like to do a transformation. So I will do a CS transformation. Okay. This is a work, so there's just extra steps, okay, to transform the values, okay, to make this more suitable for linear regression. Otherwise, you have all zeros, ones. But yeah, for the details of the transformation, you have to look at the function. That will be another long story. It's called Pearman residual transformation, but here we just put in this way, okay? And then you need to transpose your matrix. Remember to put this semicolon at the end, otherwise it will print out a lot of this raw data on the screen. So at this moment, we are prepared our regression model, input and output. So just iterate what the problem is, what our problem is. So we have this 1,299 cells expression per file regarding to 9,342 genes. Oh, we really have to have a gene name, unfortunately. Oh, the gene name is still in here, okay. So we need a G. We need a gene name, SCE, G, okay. Yeah. So at the end we will see, okay, which gene actually contribute most to this potency difference across the cells. Yeah. I recognize variable. Oh, there's no, let's transform, not a transformation. Yeah. Yeah. Good. Yeah. Good. Yeah, I will save this workspace for now. Save. Uh, Space. Regression. For regress. Yeah, this is just for safety. I just save all the variables here in a file here. So if I somehow later I get this computer crashed, I can re-log in, come back and load this workspace back. Okay. Yeah, I think we should take a 5 minutes break, and in the middle of the break, you may want to think about once we have this, what to do. Okay. Yeah, we are ready to do the regression. Yeah. But I have never tried this. I don't know what will happen. I don't know so many variables. Whether this B will save to do this, I'm not so sure. Yeah. Yeah, so I tried this during the break. It does work, and you see, you try to do this fitting and try to estimate beta values, and you do, indeed, you get the beta values, and a lot of zeros, okay? But in the middle, there are some precision problems because the model try to fit every single variables, whether they are potentially will be major contributor or not. It will treat all the genes equally. At the end, it gave some values. But I said it works fine, but numerically it's a little bit unstable. So we probably should replace this as a lasso. Lasso should have a very similar ASSO. Should have a similar structure. I didn't read the documentation, but let's see. If you replace regression with lasso, lasso use x, y instead of y, x, so we need to replace. So instead of doing regression, you can do lasso and put x in front, y. So let's see, give this beta x, okay? This will be the solution of the So lasso gave you a solution for the beta, but it's not just one solution. It gave you different levels of the selection. So if you look at the BX, the output from lasso, it's also for each column is a beta value for the regression. But when you move to the right end, you will see more zero and more zeros. Okay. At the very end, majority of this selected variable will be zero. Only the most important ones will be left with non-zero values. So, and also the lasso didn't give you the error report of this precision problem. So in our large regression model, with many, many variables like this, you have 9,000 genes. You probably want to use lasso to regularize how many returned beta you want to include in the model. So if you decide to use the most stringent cutoff and the column 64, BX 64, greater than zero, no gene has been found. So let's try 63. No. 60. So when you select at this end, this level cut off, there are 4 genes have been selected with non-zero beta values. We can check what they are. So if you do a gene, so those are the 4 genes have been selected by lasso that can be used to explain the Y, which is a differential in potency. For the linear regression, I don't know how many beta is greater than 0. So linear regression, select 633 and with non-zero variable values. Lasso can give you different solutions. If I do this, yeah, so you can decide how many genes you want to include in your model. Yeah, this is probably a little bit too much, but I just show you again, so how I get a B. So this is a regular regression, okay? Who has any problem? Question in the middle? Questions in the middle? No? Yeah, all right. Just want to know this. Yeah. BX. So yes, let's see. I just do that again. So BX will not return just one single column of B, but many columns. And it's ranked by from left to right, how many non-zeros will be included in it. Y must be the real value. Yes, let's see. Yeah, your X hasn't been transposed. Your X should be, yeah, your X has to be cell by gene.
I was transposing.
Yeah, you just transpose. Yeah, then run that again. Yeah.
Oh, cool.
Yeah, because you mess up with the genes and the cells.
Okay.
Yeah, you have to be very clear what you want to predict for. This is cell-wise, but use genes to predict cell rather than the opposite. Okay. Yeah, good. Yeah. Yeah. Yeah, so I believe your X didn't transpose correctly. Yeah. Yeah, it should be cell by gene. Yeah.
So my question is, can you use the regression learner we just learned to
Yeah, probably you can, yes.
Because it seems like same thing, right?
You should, in theory. In theory.
Oh, you can change it.
So to deal with this large kind of regression problem, you want to use lasso instead of original, because this not give you the flexibility. This returns, the lasso gave you the selection of different levels of the feature variables you want to include. How many you can decide which columns you want to use, and numerically most stable. Yeah. For small problem, just like the car, engine size, the price, the linear regression should be okay. If you have dealing with this several hundred of variables, it's still okay. Yeah, so follow our schedule. I jumped from the regression to lasso because the structure of the coding is so similar, right? You just, once you establish the matrix X and Y response variables, then you can select lasso to do that. Maybe just spend a couple minutes to look at lasso inside and see whether I remember there's some kind of tree structure, the plot. We can look at the number, set a cutoff. So this one, it returns a big B variable name, so we call Bx, it's the same. So this is 25th column, and see how many non-zeros, okay? So this small example only have 5 different variables, and the lasso select 2 of them at this column, 25 column level. There are procedures to let you know where the cutoff you should set. In our examples, we have from 1 to column 64, and you don't know where you should stop, which cutoff you should use. There's some of this diagnostic plot to show you, okay, you should stop using that cutoff to give you the balanced number of the variables, and and also the percentage of explanation of the variability in Y. Okay, I think that's what I want to get is this so-called lasso plot. So lasso plot will take the output, the beta variable, beta value matrix. So you know you can plot, you have your Bx is your output. Then if you use lasso plot, give Bx here. Let's do a new figure. Yeah, so that's your so plot. Yeah, I believe those are the individual genes beta value change across different lambda, which is yeah, how to describe this? Let's see. So they create a trace plot for the beta value against L1 norm of beta vector. So this is just one type of this lasso plot in order to let you know during the process of including variable or not, to give you the change of those penalty, L1 norm penalty for those sum of those beta absolute values. Yeah, I got confused exactly what those lines are. Okay, so this is one of these. And I believe this function also allow you to do different types of the lasso plot. Yeah, so what's this? Let me think about this. Mm-hmm. Yeah, I need to go back and look at what's in the y-axis. It's not very clear to me right now. Okay, but those purpose of those is just let you know through this fitting procedure what's this beta value change as a penalty term. And also there's some other, like the lambda plot the type will allow you to select where the cutoff should be, something like that. In the toolbox, I use lasso to search for marker genes. So I put a particular group of the one cluster of cells labeled as 1, and the rest of them labeled as 0. So I want to see, okay, which gene will give you this 0-1 prediction the best, and how many you want to use to explain this difference between 0-1. So in that case, I did a regression, but it's only 0-1 regression. Okay, use the lasso to find those marker genes. And I can specify how many marker genes I want to extract from the matrix. Here we predict the potency, which is continuous variable, so different from what I just described as a 0-1 to find the marker genes for a certain class of cells. But the same structure here. I think I want to look at whether there are some meaning of those genes. Do you think those genes are meaningful in our fibroblast samples? I only see housekeeping genes. Yeah, so we select the fibroblasts and estimate their differentiation potency, and then we use lasso to find those genes. But to me, those genes are all housekeeping genes, so it doesn't make any sense. So for this, it could only because they are highly expressed, so they have a lot of non-zeros in there, so they tend to be included in the variable model, in the regression model. I don't know. Yeah.
You don't really look at the sample of fibroblasts as a whole instead of just by each column?
The fibroblasts as a whole, yes. We include have a 1,020. We have 1,299 fibroblasts.
Which specific genes out of like the whole sample?
Out of the whole sample, including other cell types.
Just with the fibroblasts.
Yeah, so that's what we're doing. Our input is X, contains all the fibroblasts, all the genes.
Does that mean you need to remove the housekeeping gene first before you?
Yeah, so that's probably that's what I want to do. I will remove those housekeeping genes because they tend to be included in the regression model because they have values, not so many zeros. So that's why maybe the highly variable genes will be very useful. We select those genes have more variability in there. Yeah.
Can I share my comment?
Yeah.
About the plot that is created for Lasso?
Yeah.
I guess it's like similar to R square of the regression model.
Mm-hmm.
Like 60% of the R square,
Mm-hmm.
and the left column is like a coefficient, so the R betas, how each gene or variable is contributing to the model.
Mm-hmm.
So at the end, it's like 0.60. So it's like
You mean each line is one gene? It's not. It's
it's like the coefficients changes during the trials.
Oh.
So at the end, altogether, they just can describe 16%, like that. Like R square of 16. Like,
Yeah.
I don't know.
Yeah. I'm not so sure.
Dr. Davian.
Yeah. I don't know. Yeah. Yeah. So I include more genes. Yeah, I start to see NF-kappa B, the tubulin, heat shock protein. Yeah, so it looks like this analysis doesn't make any sense because they're all housekeeping genes. Maybe that's true because there's no differentiation potency among fibroblasts. They all similar level. It's not a trajectory of development or differentiation from stem cell to there. But if we change it to another system, probably this will work. But now, so far, it's just random genes, what I can see. Nothing related to the differentiation or other.
What's the difference between differentiation potency and expression level?
Expression level for particular gene, which gene? Potency. Yeah.
Means express high or what?
No, it's not expressed high. It's the state of the cell is more similar to stem cell. Non-differentiated. Mm-hmm. Yeah.
So if you close to stem cell, that means your potency is low.
Is a high. Potency is a high.
Potency is
Yeah, if it's more similar to stem.
if it's high, it means not differentiated.
Mm-hmm. Yeah.
Then the negative number, in my differentiation potency, we see this cells express more.
Yeah. So the you mean the potency value itself? This should be positive all the time.
This is all positive numbers,
Yeah.
but when I do the transform and then they become negative.
You don't have to transform.
I don't have to transform.
No, not transform the potency value.
I just transform the x.
Yeah, just transform the x. Yeah. Okay, in the last 30 minutes, we will use highly variable gene analysis. Okay. So for this particular example, we didn't find any meaningful genes. I believe it's because the cells, there's no differentiation, variability among them. It's just a group of cells that have been fully developed, differentiated. They're all fibroblasts. So, but we use algorithm to force them to give a value to make a gradient, but they're not really different. So that's why most of gene come out just based on how much information in that gene give to us. But if we replace this to a better system with cells from different time points of the differentiation, we probably can build this better values and use better systems to study this. This still be a feasible option if you decide to do that. It should work sometimes. Okay, but it depends on your why, what we want to predict for. Okay. So now we can clean this. Come back to our toolbox. I want to use example to show the highly variable gene analysis. So for this study, we need to have a homogeneous population of cells. If you have cells from different cell type, different states, and they all something like this, it doesn't make sense to predict these highly variable genes because that's variability could be from because of different cell type have different marker genes, and the marker genes will only express in 30% of the fibroblast and not in other cells. So they create some artifacts because the cell type difference, heterogeneity. We are not talking about the heterogeneity of the cell types, but we are focusing on one cell type, all the cells in the same states. So I will focus on, let's see what cell type these are. One cell type. Yeah, so this green, this light blue cluster is alpha cell. And alpha cell has two subclusters here, and we just select one of them and then to run highly variable gene detection. Okay, so that's what I'm going to do. I'm going to first rotate, so I have a good angle to select those group of cells, and then I will extract them out. So I brush the cells and make sure they're all same cell type. And then click this delete cell, I will delete unselected cell. Okay, you don't want to expand to cell group, otherwise another subset of the upper cells will be selected. So you only select those brushed cells, but then delete unselected cells. If you click the wrong button, you have to restart this example. Now, all the cells I get is from the alpha cells, that homogeneous population of the group. And after this selection, I need to remove some genes, expression level too low. I use stringent cutoff to do the QC. Okay, 154 genes removed. Use selection, your brush may select slightly different numbers of cells, so you don't have the same numbers of the gene removed as I did, but that's the. Now we can do a embedding. For example, I will try to do all of this embedding again and see whether they are a really homogeneous population. You don't want to select these two because this will take longer than the other. I'm just re-embedding the cells I selected to see whether there's internal structure if I do this independent embedding. Just make sure they are homogeneous population. There's no cell type problem. They're all alpha cells, so we are okay. So after embedding, you can view all the possible embeddings you have already. Yeah. Yeah. So you got lost by a select subgroup. Yeah. So you brush. Yeah, you brush. You found a group of cells, yeah, whatever. Good. And then you see delete, yeah, delete unselected. Then you have that, this homogeneous. Then you want to do a QC. The QC again. Say okay. Mm-hmm. Yeah, basically you have that. Mm-hmm. Yeah, we are ready to do. Yeah, if you don't want to do re-embedding, it's fine. So this is the re-embedded. You see, Tisney and UMAP all gave me just one cluster of cells. Looks pretty homogeneous. But the fate gave me some of the structure. If you decide to go further, say I can only extract cells from this region, that's okay. But so far, based on the UMAP and Tisney, we are okay. So this population just emphasize this like very, very homogeneous. Okay, once you have this, you are ready to do the highly variable gene analysis. You need to click this button, okay? So this analysis will work on this homogeneous population and then extract those highly variable genes out of it. And then we will have a list of genes and send it to the enricher analysis to see what the function of those genes are. So you click this, and after the reading of this, all the cells will be included. That's right, because we know they are homogeneous. And then you use spleen fit. There's some problem with this. Okay, in this figure, on your left is this 3D plot. Each point is a gene. Okay, I can highlight those genes. So the genes jump away out of this regression curve in the orange. Those are the highly variable genes. So we can, for example, highlight this gene, the DAPL1, and its expression profile across the cells will be showed here, and you can know why it's highly variable. So PPT is here, PYY is here, and if you select the gene within this curve, you see a very different pattern here. Okay, so the genes on this curve are the non-highly variable genes, where genes jump out from here are the highly variable genes. And the next depends on, you can select, just highlight those highly variable genes. I will see 150 of them, 150. Okay, so those genes were selected based on the distance. This gene was not selected because their expression level is just too high, and I intentionally ignored some of those highly expressed genes. Okay, now once you select these 150 genes, or less or more, you can start to send you can save their names. You can click this button and to do an enricher analysis. So this button will send those gene names. Oh, something wrong with this. Yeah. So there, I have to fix that part. Mm-hmm. Oh, you didn't delete them.
I pressed.
Yeah.
You guys did.
Yeah.
Okay.
Yeah, I'm pretty sure you use an older version of this program. Yeah, let me try. Yeah. 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 Okay. Yeah. Yeah. I'm pretty sure you use an older version of this. Let me see. Yeah. Yeah. This is very old, so you want to use a new version by reinstall. Yeah. Yeah. Yeah, so I have a problem here, and I cannot do enricher directly, but I will fix that problem later. But once you have those gene names, you can export those names. Save these names using one of the buttons here. And then you collect those gene names and put into enricher or other enrichment analysis to see whether they have a function enriched. Yeah, for some reason I have this errors. Yeah, so I have a problem to export the name of these genes. Yeah, this is a bug that should be fixed, but for now you can only have some idea what those genes are.
You can save them to the workspace.
Can you? Okay, that's good. No, I tried. I have a problem. Are they? Okay, yeah. So these are the. Oh, that's good. So at least you have some gene name to play with. So those genes has been. This table has been sorted by whether they are highly variable gene or not. The top one is the most highly variable gene we believe based on the analysis. So you can select those, and you can select those genes to do the enricher analysis if you decide to do it. Okay, you can copy the name of those genes. Yeah. Thank you, Victoria, and that's helped. But I need to fix that bug, so you can just click and to run. Okay, to do this, I have to replace my get rid of those quotations and copy this and go to enricher, enrich R. So this is a program. You can paste your gene. You put the gene names in there. Yeah, so I don't know whether those serine type endopeptidase activity related to the alpha cell function. I'm not so sure, but this just gave you a suggestion that those genes, for example, the highlighted in the pop-up this bar, the names, those genes, as a group, they are highly variable expressed in alpha cell in that particular cell cluster. Yeah, I can Google this again, alpha cells. Yeah, I try to learn some biology out of this, see whether there's some relationship with alpha cells. So far, I didn't see too much the difference to the bacterium. I don't know. So yes, a lot of immune-related genes have been selected for. Okay, that's a way you can try apply to different cell type. Remember, it has to be homogeneous population of cells in order to do this. See whether those active genes you found make sense to explain the function or potential function of the cells under the study. What I can see is a lot of cells, they are alpha cells, but they start to show some immunity-related properties like defense response. Okay? This could be true, could be the false positive results, but you have to read the literature, see where those alpha cells were collected from, what type of mice. If you read those studies, probably it start to make sense. I don't know yet. Okay, so those studies from this gene set, this data set. This is a study of yeah, I don't know what kind of treatment, whether they have already. Yeah, so there's some of these procedures probably triggered some of those response. I don't know, but that's hypothesis. Okay. All right, I think that's all the items that we finished them all, and let me know if you have any questions before we leave. Yeah, Vicky. Mm-hmm.
In the end picture, while we are hovering on each pathway, we are able to see the genes, right?
Mm-hmm.
Can we get the gene list without hovering?
Yeah, you can export the Excels. I'll show you. If you want the whole table.
Yeah, the whole table with the genes. Can we get that?
With the genes,
like
yes.
Suppose if we are hovering on this pathway.
Yeah.
Yeah, like so we want go to
yeah, the table.
Yeah, and yeah, so we are getting all the genes which are upregulated or downregulated.
Yes.
So
I think it's right here.
Okay, if we export, can we? Okay.
Oh, sorry. This should be all there. So the first row, and you should have that genes.
Okay, okay.
Yeah, so it's an exported table in the for your
Okay.
downstream. Yeah.
Can we also see in the Metascape?
Metascape.
Yeah, Metascape.
Yeah, Metascape is the same. You can also post it there, see which. Yeah, Metascape also very comprehensive. Yes.
We can also see the gene names.
Yeah,
similar.
you should. Yeah.
Okay.
Yeah.
But both will be similar, right? We'll get the same number of genes.
Mm-hmm. You should.
Both.
Yeah.
Okay. That's it.
Yeah.
Thank you.
Yeah.
Are you using the email for that site?
The Yongjian, yes. Let me send to you. That's his email. You just take a picture.
The top one.
Yeah, the top one.
And did you say I should email someone about the actual MATLAB part not working, or that was probably the VIBS?
I will fix that
That's
very
it.
soon.
Okay.
Yeah, yeah.
Awesome.
Yeah, pretty.
Thank you.
Yeah, thank you.
Dr. Pat
Mhm.
reinstalled it, and it still did the same thing, and then the computer shut down. So I just,
Yeah.
so
Yeah.
I just left the computer as is.
Mhm.
Um,
But you have a Windows machine, right? That's Windows. You shouldn't. You can just reinstall that package. Yeah, it should work.
my other question for you is completely not like your responsibility, but like